Subscribe now.
You are welcome back to today's tutorial on discrete Fourier transform. And today we are going to talk about the decimation in time fast Fourier transform algorithm, which is DIT. Right, DIT. For this tutorial, I'll explore the DIT FFT algorithm, which is one of the most common algorithms used to compute the FFT efficiently, right? So these are some of the key points that you should take note of. The concept of decimation in time FFT algorithm, which is DIT FFT algorithm, is in the fact that this algorithm is a specific implementation of the FFT, and it utilizes a divide and conquer approach, as I told you in my previous tutorials. It also divides the DFT calculation into smaller DFTs, and also it starts from the input sequence and continuously divide it into a smaller sequences until it approaches the case of DFT of the size 2. That's what we call the radix 2. The algorithm also then combines these smaller DFT that it has computed to the final DFT of the input sequence. And one strategy in the decimation in time is that the decimation in time, which also refers to the process of dividing the time domain sequence into smaller sequence. You will get to know why it is the process of dividing the time domain sequence into smaller sequence in no time. So in the DIT FFT algorithm, the sequence is actually decimated into even and odd indexes. So if it's maybe we have 0, 1, 2, 3, 4, is divided into even and odd indices. It can be 0 and 2, it can be 0, 0 and 4, and it can be 2 and 4, right? I will show you how this decimation is being done, right? And these are the process, these are then processed separately and combined to compute the DFT, right? So basically, this DFT is very efficient. DIT FFT algorithm is very efficient. I said it's highly efficient with a computational complexity, as I said earlier on, reducing the number of complex multiplication and the number of complex addition into a smaller chunk. And therefore, I will say that this efficiency makes the DIT FFT algorithm ideal for real-time and high-performance application where fast computation is very crucial over there, right? So, as we are going, I'm going to show you some small derivation of how the even and odd decimation is being done, and I will demonstrate the step-by-step process of calculating this DIT FFT for a simple signal to illustrate how the algorithm works in practice, right? This example that we also do after the derivation will also help you to understand how the recursive nature of the decimation time FFT algorithm and how it efficiently compute the discrete Fourier transform of the input sequence. So let's go straight without wasting much time to look at how the derivation behind the decimation in time algorithm. So as I said earlier, we will split the input sequence into even and odd indexes, right? So we all know we are going to start from this angle. We know the general formula of x of k to be equal to summation of n equal to 0 and then n minus 1 x of n, and then omega n k of n, where this one is a trade-off factor with the power k of n, k and n. So based on this, if we want the input, which is n, to be only even, the function that we can come up with is n equal to 2m. Let's test it whether the function that we have come out with is correct. For n equal to 0, we can get n equal to 2 times 0, which is equal to 0. When n equal to 1, we can get 2 times 1 equal to 2. When n equal to 2, we can get 2 times 2 equal to 4. When n is equal to 3, we can get 2 times 3 equal to 6. As we can see, it gives us even outputs irrespective of what the input will be, right? So if we want the decimation, we want to group the sequence into odd and even, we need to come up with a function to be as our input. So instead of putting the n as a variable over there, we will put the 2m, and then that 2m is going to serve as our input even sequence, right? So instead of writing the general formula like this, we can also write the general formula as x of k equal to the summation of m equal to 0, and then n over 2 minus 1. And I did n over 2 minus 1 because if we have n equal to 4, of which the samples is 4, if the sample is 4, it can be, let's say, 0, 1, 2, 3. If I divide this one into both even and odd, I'll get the even as 0 and 2. I also get the odd as 1 and 3, and therefore my number for the even aspect is the total number over 2, which is 2 samples, which is 0 and 2. And then my number for the odd sample is going to be n over 2, which is also 1 and 3. And therefore, it's the upper part is not going to be n minus 1 for the even decimation computation, but it's going to be n over 2 minus 1 for the even computation. Right, so looking at the even computation aspect, for n over 2 minus 1, x of now the input function is 2m, which stand for the even numbers, right? And then we are going to get our omega n, and then remember that we have kn over here, kn over here. So if there's kn over there, then since n is equal to 2m, we are going to get 2m k. I hope you get this. So now this is the even aspect. So let's come to the odd aspects. So now we have been able to, if we take this as an example, we have been able to decimate into for the even. So if we want the odd aspect, considering this same example over here, the function that we can come out is 2m plus 1. For the 2m plus 1 means that if n is equal to 0, we are going to get 2 times 0 plus 1, of which we are going to get 1. If m is equal to 1, we are going to get 2 times 1 plus 1, which is equal to 3. And for n is equal to, let's say m is equal to, let's say 2, we are going to get 2 times 2 plus 1, which is equal to 5. So in that case, we will be able to get all the odd number sequences, right, out of it. So therefore, we can come into conclusion that the odd number aspects of the DFT can be written as n over 2 minus 1 over here of x into bracket 2m plus 1 of n, and then 2, let's write it here. You know that I was telling you that this part was nk, and because n is equal to 2m plus 1, we are going to get k into bracket 2m plus 1 over here. I hope you understand it up to this stage. Now let's proceed to know what we have already. Now we can we can combine the total DFT formula as m equal to 0 of n over 2 minus 1 x of 2m omega n 2km, right, plus the summation of m equal to 0 to n over 2 minus 1, and then x 2m plus 1, and then omega n k, the omega n 2km. People may not understand, so let me try and go in step by step. Let me write here 2k into bracket what, 2m plus 1. You get me? So let's take them one after the other, right? So if you are taking them one after the other, we can do something like this. But before that, let's consider this property. We know that our omega n over here is equal to exponent negative j 2 pi on n, where k is equal to 1, because by the trade-off factor property, omega n k is equal to exponent negative j 2 pi over n k. That's what we know from the previous tutorial, right? So where k equal to 1, you are going to get omega n equal to exponent negative j 2 pi over n. So when k equal to 2, we are going to get omega n 2 equal to exponent negative j 2 pi on n multiplied by 2. So multiply by 2 means that this one, I can also write this same exponent as omega n of 2 equal to exponent negative j 2 pi over n over 2, right? This one is, let me write it word so you see it, negative j 2 pi over into bracket n over 2. This has been written as this. This has been done because with this, when I want to write it in the normal way like this, I can also do it as negative j 2 pi multiplied by, right, 2 over n. Or let me do it this one way. You can do exponent negative j 2 pi divided by n over 2. If I want to do multiplication, I need to reciprocate it. And when I do the reciprocation, I'm going to get exponent negative j 2 pi multiply by 2 again on n. So this means that I can write it as in this form. If I can write it in this form, then I can say that then omega n of 2 is equal to exponent negative j 2 pi over n on 2, and then therefore I can write this n here also in this form. So I hope that's one clears. So this means that omega n of 2 or wn of 2 is equal to wn over 2, of which n is equal to n over 2. So now that we have got a clear understanding of this property, we can employ the same up there. So looking at the fact that the even part is x of k will be equal to the summation of m equal to 0, and then n over 2 minus 1 x of 2m omega n of 2km, right, of 2km. It can also be rewritten as x of k equal to summation of m equal to 0, n over 2 minus 1, and then x of 2m, right, omega n of 2 multiplied by omega, let's say I don't have to even divide it, of 2 multiplied by what, km. We know that this omega m of 2 here can also be written as omega n over 2 or wm over 2, and therefore s of k it's equal to summation of m equal to 2 n over 2 minus 1 x of 2m, and then we can write w n over 2 then km. So I hope this one helps here. So let's look at this is the even aspect. Let's look at the odd number aspect. X of k equal to the summation of m equal to 0, n over 2 minus 1 x of 2m plus 1, and then we have the omega or the omega or the w to be of k into bracket 2m plus 1, and I said we should have to expand this part. When we expand it, we are going to get summation of m equal to 0, n over 2 minus 1 x of 2m plus 1, and then we see omega. Oh, this one didn't write well. And then omega 2km plus k, and this can also be expanded as equal to 0, n over 2 minus 1 x of 2m plus 1, and then we can expand here. We know that this one from the even part can also be rewritten as omega right, n, and then over 2 km. And then from there, we can also multiply by omega k here, right? You can also multiply by omega k or wk over there. And based on that, we can say that in case we are making g of k to be equal to the even part, which is m equal to 0, and then n over 2 minus 1, x of 2m, omega n over 2 km, then this is the even part, of which the even part I illustrated it for you to see up there. That's the even part, the discrete Fourier transform of the even sequences, right? This is the part. And we can also say that the discrete Fourier transform of the odd sequence inside the given sequence can also be represented by m equal to 0, n over 2 minus 1, and then x of 2m plus 1, and then omega k m, and then n on 2, right? This is what it will represent. So in case we are representing all of them together, we are going to get x of k to be equal to the even part, which has been calculated over here, and then the odd part, right, which has also been calculated over here. But remember that there's a 1 omega k attached to it, so it's going to be plus omega k h of what? K. So this is final derivation of the even and odd decimation of the decimation in time method. So in case we are applying the symmetric property, we can say that our g of k is equal to g into bracket k plus n over 2. When you say the symmetric property, if it means that if here it's 1, the other side is negative 1. So if I have something on the Cartesian plane and I have one line located here, the symmetry of this line, right, the other side of this line should be here. That means the two lines should be symmetrical, right, about the origin, the line at the origin. So if we are applying the symmetric property that we derived in my previous video, we can say that k is equal to k plus 1 over 2, and then 1 over 2, and then the k can be equal to 0, 1, and 2 up to n over 2 minus 1, right? And then when we apply it on the general one, we can see that our k plus n over 2, right, is equal to gk, right, minus omega nk h of what? K. This is what we have, because we are aware for the property that omega n of 2 plus k is equal to negative omega n k, right? That's equal to negative omega n k. So if we have the one for the positive side, then obviously the other one moving to the negative side. So looking at it, this one here made the negative sign over here. So to conclude, we can say that the two parts, or the two symmetric properties, that the symmetric property is that if you have the decimation in even numbers, right, the first part, if it takes k plus n over 2, right, let's say 0 and 2 as a combination, it will have two parts. The first part will be j of k, right, plus omega n k h of k, and the second part is going to be sk plus n on 2 to be equal to j of k minus omega n k h of k. So this is the symmetric property that we're talking about. It's very crucial, very important. Yes. So these are the two iterations that I wanted to show you. These are the two iterations that I wanted to show you for the g of k to be equal to m equal to 0, and then n over 2 minus 1, x of what? 2m, which is the even part, omega n on 2, and then km, and then the odd part, k, to be equal to summation of m equal to 0, and then n on 2 minus 1, x of 2m plus 1, and then omega. Yeah, that's the j of k. Let's say h of k. So we have not added the other one. So let's look at something here. These are some cases that we can consider as well. If we have number of points to be 2, which is 2 sequence, then we can say that our k will be 0 up to 1. The summations will be up to 0 up to 1, right? Then we can use this 2 symmetric property here and say that our x of 0 is equal to g of 0 plus omega 2. And remember that this part is what? K, right? 0, and the k is 0 because k is 0. And then multiply by h of 0. So if in case our sequence is n equal to 1, 0, 1, 2, 3, now here becomes our g of 0, this one becomes our g of 1, and this also becomes our h of 0, and this one becomes our h of 1. You get it? Come on, h of 1. So based on that, you can see that the combined one is going g of 0 is 0, right? Plus w 20, and per my previous tutorial we said that w power n and then power 1 is equal to exponent negative j 2 pi on 2, and which is equal to exponent negative j pi, right? So when we simplify this, you are supposed to get what? 1. You get me? So when you get it, that is very important here. When you get it, that's omega 20, because the k is 0, everything here goes to 0, and then we are going to get 1. So when we get 1, we are going to get g of 0, right? Here is 0, and then here is 2. So 1 multiplied by h of 2. h of 1 is also what? h of 0 is also what? 1. And then we are going to get 1 in case we are using this as an example. But that's not our focus for now, right? So my focus is that our x of 0 is equal to g of 0 plus omega 2 of 0 h of 0, which is equal to x of 0, right, plus omega 2 of 0 x of 1. That's what you need to understand. And its counterpart, which is this mirror image or this symmetric part, is also x of 0 plus 1 is equal to g of 0 minus w20 h of 0, which is equal to x of 0 minus omega 2 of 0 x of 1. So if you are computing the FFT of this, you don't need to compute both. You can compute this one and then change the sign for this and write the answer as well. So this is the hidden secret behind that. So without wasting much time, we are going to introduce you into decimation in time using the main algorithm, which is the butterfly diagram. So thank you for watching this video, and see you in my next tutorial.